And so what's actually happening here, you might ask the question, well, why aren't these all reacting? And the reason is very complex and probably not going to get to the full reason today. It's going to involve us understanding a lot more about something called the collision model of reactions. And but for now, I'm just going to tell you that one of the things that's happening in this reaction that we haven't talked about is that these iron thiocyanate complexes that are being formed are also breaking back apart. You have a forward reaction creating the red, but you also have a backwards reaction getting rid of the red. And so inside of this solution right here, right now, we have iron thiocyanate complexes being formed, being created, and iron thiocyanate complexes breaking apart. So you should expect it to get darker red or lighter, but it's not. Why not?
Because they're breaking and forming at the same rate.
Exactly. They're breaking and forming at the same rate. That's exactly the way to say it. And so the forward reaction, the creation of iron thiocyanate complex, red, and the backwards reaction, the removal, the breaking apart of iron thiocyanate complex, getting rid of red, are happening. They're both happening, but they're happening at exactly the same rate. It's as though, imagine that the birth rate and the death rate in a country were exactly the same. You'd have the same number of people all the time, but they wouldn't be the same people, right? You'd have dead people and new babies and all these kinds of things. It's the same idea. This kind of reaction where you have a forward and a backward, where it can go forward or it can go backwards, is called a reversible reaction. This is a reversible reaction. And if the forward and backwards reactions are happening at the same rate so that there's no overall change in the concentration, there's a word for that. What do you call a reversible reaction where the forward and backward reactions are happening at the same rate? That's right. We call it equilibrium, the big word in red on the back wall there, equilibrium. That's what equilibrium is. Equilibrium is a dynamic system. Everything is changing. Things are changing all the time, but the overall reaction concentrations remain the same. Now, if I take a dynamic system like this, where everything's changing back and forth all the time, and I mess with something, for example, let's say that I removed thiocyanate ion. Okay? Let's say I just somehow magically went in and sucked all the thiocyanate ions out of it. What should happen to the reaction then, if these don't exist anymore?
It just stays iron, right?
So, and this gets into the collision model. I don't want to. Maybe I'm getting into too deep of a question. So let me not ask that question. Instead, let me show you. I can, through magic wizardry, remove the thiocyanate ions. I have a little magic here called mercury chloride. And mercury ion binds to the thiocyanate ions, basically makes it unavailable to the reaction. And here's what happens. See what's happening here? What's that doing?
Taking all the red from the shaft or something?
Yeah, it's getting rid of the red. It's getting rid of this stuff. So removing this stuff, getting rid of it, gets rid of this stuff somehow. It's kind of weird, isn't it? But if you think about it, it's not that weird, because remember what's happening. You're using this to make this, and at the same time you're using this to make this, right? Well, if you get rid of this, can you make any more of that? No. But didn't we just say this is always breaking down? So if we get rid of this can't make more, but this is still breaking down, shouldn't this go down? And so that's one of the first illustrations of something called Le Chatelier's principle, which you don't need to write down. We'll talk a lot more about it next time. But that's the very first example of a really important concept in equilibrium called Le Chatelier's principle. And so this is kind of a way to get you thinking. Now, I think we'll go ahead and stop there.